let's start with an introduction to the idea behind the inverse design approach, which we use throughout this presentation. And as you can see in this workflow, these are the inputs that are used by the inverse design method to give us the final blade design. So apart from some basic parameters, these blade loading inputs are really flow related. And so once you have a good understanding of your specific flow issue, whether it's secondary flow or corner separation or cavitation that you're dealing with, it's possible to come up with guidelines on the optimum blade loading to tackle each of these issues. And actually, this know-how has generality, which makes it suitable for all your pump applications. And so what's interesting then is that you only need to rely on your knowledge of flow physics, and then this method will work for you regardless of your pump size or which specific speed regime it falls under. And so this makes the entire process very intuitive and removes any empiricism that's commonly seen in conventional design methods. So now let's look at the design of pumps in a bit more detail. So across the specific speed range, pumps are subject to various flow phenomena and loss mechanisms which are dominant in that particular range. For example, as you can see in this specific speed chart, leakage and secondary flow effects are more dominant in the lower ranges, whereas profile losses and corner separation in diffusers take priority in the higher ranges. Also, a phenomenon such as cavitation can really affect pumps over the entire specific speed range. And this is something that must be dealt with on a case basis. So the question really is whether it's possible to come up with a set of optimum design guidelines based on these fluid dynamic considerations of reducing the dominant flow losses for your pump.